let's say we wanted to find the integral from, I don't know, 3 to 7 of 1 over the square root of x minus 3. So let me move this up a little bit here. Again, just like before, this might not immediately present itself as being improper. Right? We have to recognize, oh, look, that function is undefined when x equals 3. So we're going to rewrite this as the limit as a approaches 3 of the integral from a to 7 of 1 over the square root of x minus 3 dx. And actually, there's one other tiny thing we should do, which is that we should actually say its limit as a approaches 3 from which side? Well, if we're between 3 and 7, we're in here. What side of 3 are we on? Right, I would say the right side, but yeah, we are on the right. We're going to have this little positive thing up here. We're on the bigger side of 3. So usually we should do that. And then we're going to integrate this. I would probably rewrite this as the limit as a approaches 3 from the right of the integral from a to 7 of x minus 3 to the negative 1/2, and then do the antiderivative. We could do a u sub here, but we really don't need to. We can just antidifferentiate that straight away and get the limit as a approaches 3 from the right. The antiderivative of x minus 3 to the negative 1/2 is x minus 3 to the positive 1/2 divided by 1/2, or times 2, evaluated from a to 7. And then we plug in our limits of integration. We get the limit as a approaches 3 from the right of 2 times 7 minus 3 to the 1/2 minus 2 times a minus 3 to the 1/2. And now when we plug in 3, what's going to happen? Well, we're going to get 2 times 4 to the 1/2 minus, if I plug in 3 for a here, I get 3 minus 3, which is 0 to the 1/2 power, and the square root of 0 is just 0. So I end up getting 2 times the square root of 4 minus 0, which is just 4. Let's contrast this with a similar but different problem. So let's see, I can probably fit this in here, yeah. So let's try another one. Let's try the integral from 2 to 6 of 1 over x minus 2 cubed. So same idea, right? This function is definitely I should say, not the function, the integrand, right? The thing we're integrating is definitely undefined at positive 2. So we're going to say that this is equal to the limit as a approaches 2 of the integral from a to 6 of, and I'm going to rewrite my integrand because right, why not? X minus 2 to the negative 3rd. And then of course, if I'm between 2 and 6, a should be approaching 2 also from the right side, right? If I'm between 2 and 6, I'm definitely bigger than 2. Okay, same idea here. We're going to anti-differentiate this. We're going to get x minus 2 to the negative 2 divided by negative 2. I forgot to write something. That's okay. I also need the limit as a approaches 2 from the right and the limits of integration, which are a 6. Questions so far? People good on Zoom? Stop me if you have questions. So then, just like before, we're going to plug in, and we're going to get 6 minus 2 to the negative 2nd over negative 2 minus 2 minus 2. Oh, sorry, it's the a minus 2, apologies, to the negative 2nd over negative 2. The reason I want to do this one is because it's really easy to come to an incorrect conclusion here. Right here, I'm going to get 4 to the negative 2nd over negative 2. Right? So this is going to become, I don't know, negative 1 over 16, I think. Negative 1 over 32, if I multiply by 2. But what about this part over here? If I plug in a equal to 2, I'm going to get 2 minus 2 to the negative 2 over negative 2. And it's really, really easy to think that 2 minus 2, which is 0, to a power is going to be 0. But it's not, right? 0 to a negative power is like division by 0. So here, this part here is going to go to some sort of infinity because we're having division by 0. So here, I would say that this is equal to, I don't really care about the negative 1 over 32. I have minus, essentially, what that's going to be a positive infinity because my thing is slightly larger than 0. So I have essentially, oh, but it's negative there. Sorry. So minus minus is plus, and then you have 0 to the negative 2 over 2. But this thing here, that's going to infinity. So I would say that this integral diverges. Specifically, diverges to infinity. So what I'm trying to emphasize is here, be careful, right? When you're getting something that's 0, 0 to a negative power is undefined. 0 to a positive power is totally fine. That's why this one over here, when we plugged in, we got 3 minus 3 to the positive 1/2, no issue, it's 0. 2 minus 2 to the negative 2, that's an issue, we get undefined. That good? Cool, okay. Let's look at a couple more. I can make this one really extra terrible, but I'm not going to make it really extra terrible. Let's look at the integral from 1 to e of 1 over x natural log of x. If you look at this one, you might think to yourself, James, this isn't undefined anywhere, right? We're totally good, but we're not. This is totally undefined where? I mean, you could say 0, you would be correct, but 0 is not between 1 and e. Where else is this undefined? If I plug in e, let's see. Now, what's natural log of e? Yeah, that's where it's undefined. It's undefined at 1 because the natural log of 1 is 0. So we need to rewrite this as the integral from a to e of 1 over x natural log of x dx. We're going to have the limit as a approaches 1 to the right. Now, this integral is going to be a little more complicated than our previous ones, right? We're going to have to do integration or use substitution. So what I would probably do is off on the side. I don't want to write the limit and the limits of integration every time. So I'm going to do my indefinite integral over here. So the integral of 1 over x natural log of x is going to be, let's see, we're going to let u equal the natural log of x. Du is going to be 1 over x dx. So this integral is going to become the integral of 1 over u du, which is going to be the natural log of the absolute value of u, which is the natural log of the absolute value of the natural log of x. So that's what we've got there. So then we can throw that back in here and say, okay, now we've got the limit as a approaches 1 from the right. We know that the integral now of 1 over x natural log of x is the natural log of x from a to e. And then if we plug those in, we're going to get the limit as a approaches 1 from the right of the natural log of the absolute value of the natural log of e minus the natural log of the absolute value of the natural log of a. And then we have to evaluate the limit. So this part, let's see, natural log of e is 1, and as we just saw, natural log of 1 is 0. So that's 1, and then the natural log of 1 is 0. And then as a approaches 1, the natural log of 1 is 0. And then as the insides go to 0, what happens to the natural log? Now, what happens to the let's see. I think about the natural log function. As x goes towards 0, the natural log function goes down, 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 down to negative infinity. So this is actually going to go to negative infinity. I should say that part goes to negative infinity. So we actually get something that's going to positive infinity. Welcome. Thank you. So this definitely diverges as well. let's look at a couple of those. So sometimes people like to do really horrible things and give you a problem like this. The integral from, let's say, let's go from 1 to infinity of 1 over the cube root of x minus 4. So clearly we have a problem where? 4. Where else do we have a problem? What's always a problem? Infinity. Infinity is always a problem. So the thing, so we're not, well, we might do this one, but let me point out how we'd have to break this one up. We definitely have to break it up at 4. So I'm going to say this, you know, from 1 to 4, 1 over the cube root of x minus 4, plus then I also have the integral from 4 to infinity of 1 over the cube root of x minus 4. But like we saw last time, an integral can't have 2 problem endpoints, and both 4 and infinity are problems. So this one here we have to break up again at any kind of convenient point. So I'm going to write this as the integral from 1 to 4 of 1 over the cube root of x minus 4, plus the integral from 4 to, I would probably pick 5. And the only reason I pick 5 is I know that if I plug in 5 minus 4, I get 1, and that's easy to evaluate. You can pick anything though that's bigger than 4. And then I'm also going to have the integral from 5 to infinity of 1 over the cube root of x minus 4. Okay. This is where good planning makes all the difference. So we've got a lot of pieces here. If one of them is divergent, the whole thing is going to diverge. So we could certainly start to write this out as the limit as b approaches 4 from the left of the integral from 1 to b. And I'm going to rewrite this instead of as 1 over the cube root of x minus 4 as x minus 4 to the negative 1/3 power. And then here I'm going to have the limit as a approaches 4 from the right of the integral from a to 5 of, again, x minus 4 to the negative 1/3. And then finally, I'm going to have the limit as, I'd probably use something other than b because I already used b. So let's say the limit as d approaches infinity of the integral from 5 to d of x minus 4 to the negative 1/3 dx. All right, so here's what I would do. Here's what I would think about. I know that when I integrate x minus 4 to the negative 1/3, I'm going to get x minus 4 to the positive 2/3 divided by something. I don't really care what. But I know that when I have x minus 4 to the 2/3, when I plug in 4, that's going to be 0 to the 2/3, which is 0. And here, the same thing. When I plug in 4, I'm going to get 0 to the 2/3, which is 0. But here, when I integrate x minus 4 to the negative 1/3 and get x minus 4 to the positive 2/3, and then I try plugging in infinity, I'm going to get infinity to a positive power, which is going to be infinitely large. So if I had to pick one of these 3 pieces to start with, I'm going to pick that one because I'm pretty sure that piece diverges. And if that piece diverges, I'm done. I don't have to look at the other 2 pieces. So let's look at this piece. So if we look at the limit as d goes to infinity of the integral from 5 to d of x minus 4 to the negative 1/3 dx, we're going to get the integral, the limit as d approaches infinity. The integral of x minus 4 to the negative 1/3 is x minus 4 to the positive 2/3 divided by 2/3 from 5 to d. Plugging in, we get the limit as as d goes to infinity of 3/2 times d minus 4 to the 2/3 minus 3/2 times 5 minus 4 to the 2/3. And then as d goes to infinity, this part's going to go to infinity. So I'm going to get infinity minus 3/2 times 1, which is infinity. which means this part diverges, which means the whole thing diverges. So the entire integral from 1 to infinity of 1 over the cube root of x minus 4 diverges.
No, the limits go to 0, right?
No, not quite. So, well, so I should say, when you plug in the 4, you'll get 0, but when you plug in the 1, you'll get something that's not 0. So the other limits will have a 0 in them, but this whole integral here will be something finite. This integral here will also be something finite.
So like when we have like multiple limits, we usually choose the one that goes to like infinity.
Not necessarily. You choose the one that you have the best guess is going to diverge. You might be in a situation where none of them diverge, or you might have to calculate all of them. But if I think one of them could be divergent, that's the one I'm going to try and pick, because I know if it diverges, I don't have to do any more work. Let's look at another one. And then we'll start talking about some midpoint and trapezoid rule stuff, because I think that's what everyone's working on. So let's look at the integral from 4 to 9 of 1 over, oh, not 4 to 9, 4 to infinity, apologies, of 1 over x squared minus 9 dx. Try to keep things numbered, keep things in order later on. So, definitely improper. So they're going to write this as the limit as b goes to infinity of the integral from 4 to b of 1 over x squared minus 9 dx. But now I have to actually integrate that thing. And how do I integrate 1 over x squared minus 9? It's definitely not the natural log of x squared minus 9. If I did that, I get the derivative would be 1 over x squared minus 9 times 2x. So what method do I have to use? What method could I try to use? I could try a u sub. If I let u equal x squared minus 9, my du is 2x, and I don't have a 2x. So if we've got a rational function, and u sub doesn't look like a possibility, what's the next thing we go to? Partial fractions. To use partial fractions, we have to make sure we meet all the requirements. The top degree has to be smaller than the bottom degree, check. And the bottom has to factor, which it does. So we're going to rewrite the partial fraction decomposition as, let's see, I have 1 over x squared minus 9 factors as x minus 3 times x plus 3. And that's going to equal a over x minus 3 plus b over x plus 3. And then that's, we're going to multiply both sides by the common denominator. We're going to get 1 on the left equals a times x plus 3 plus b times x minus 3. And then we're going to pick nice values of x. If I pick x equal to -3, I'm going to get 1 equal to a times 0 plus b times -6. So I get b equal to -1/6. And if I pick x equal to +3, I get 1 equal to a times 6. So a is equal to 1/6. Great. So I can rewrite this integral as the limit as b goes to infinity of the integral from 4 to b of, let's see, a is positive 1/6. Let's just factor out the 1/6. Instead of saying 1/6 over x minus 3 minus 1/6 over x plus 3, let's say it's 1/6 times 1 over x minus 3 minus 1 over x plus 3. Great. Questions? Okay. So now we're going to integrate. We still have the limit hanging out in front and the 1/6. The integral of 1 over x minus 3 is the natural log of the absolute value of x minus 3. The integral of 1 over x plus 3 is the natural log of the absolute value of x plus 3 from 4 to b. And then we're going to plug in our limits of integration. So we're going to get the limit as b approaches infinity of the 1/6 times the natural log of the absolute value of b minus 3. You don't really need the absolute values here since b is going to infinity. B minus 3 is certainly positive, but it's also fine to write them. Minus the natural log of the absolute value of b plus 3. And then we're going to have minus The natural log of 4 minus 3 is the natural log of 1. That's going to be 0. Minus the natural log of 4 plus 3. That's the natural log of 7. Okay. Now this is a common, teachers kind of love to ask this question because it tests your ability or your understanding of what's really going on. If we take the limit here, you might think this diverged. Because if you plug in b going to infinity, you're like, oh, natural log of infinity minus 3 is natural log of infinity, which is infinitely large. And that is true there. And then you might make the unfortunate mistake of saying, oh, we're done. Got infinity, it diverges, don't have to look at anything else. Well, it's not entirely true here because we're not saying it's one integral that's divergent. We're saying we got one part of this limit that's going to infinity. But this part here is also going to infinity. Right? This is going to infinity, this is going to infinity. And when you have infinity minus infinity, that limit is indeterminate. We have to do something with it. Right? So we're going to simplify this expression to see what's actually happening. So check this out. We get the limit as b goes to infinity of 1/6 times. I can smash these natural logs together. Instead of saying it's natural log of b minus 3 minus natural log of b plus 3, I can say it's the natural log of b minus 3 divided by b plus 3. And I did drop the absolute values because everything is positive, so I don't really need them. Minus a minus is plus the natural log of 7. Okay, now, as b approaches infinity, what happens to b minus 3 over b plus 3? What does it get really, really close to? Natural log of it does. Let me ask you all a different question real quick. I know you know the answer, you've just forgotten you know the answer. What's the limit as x goes to infinity of 2x squared plus 3x plus 7 over 5x squared minus x plus 1? What's the limit of that? Maybe you don't remember. It's okay if you don't remember. So the limit of this, the really, really easy way of seeing what it is it's 2/5. Because what's happening in that rational function there is the x squared terms are kind of dominating everything else. If x is 1,000,000, 2 times 1,000,000 squared over 5 times 1,000,000 squared, those are the only terms that really matter. The other terms, like 3 times 1,000,000 and 2 and minus 1,000,000, they don't contribute enough to really make a difference. The kind of longer way of doing this is to divide everything by the highest power of x. So if I divide everything by x squared, this is equal to the limit as x goes to infinity of 2x squared divided by x squared, 3x squared divided by x squared, 7 divided by x squared, over 5x squared over x squared, minus x over x squared, plus 1 over x squared. And all these things being divided by x, or x squared, are going to get super duper small. So the shortcut for this kind of limit is that if you have a rational function and your variable is going to infinity, the limit's going to be the leading coefficient on the top divided by the leading coefficient on the bottom. In this particular example, 2 divided by 5. In this particular example, 1 divided by 1. So this ends up equaling the 1/6 times the natural log of 1 plus the natural log of 7. But the natural log of 1 is 0, so we literally just end up getting the natural log of 7 over 6. So this integral converges. And it converges to the natural log of 7 divided by 6. It's kind of cool. So what I would say is if you see a problem where you have to do partial fractions and then you get some natural log stuff at the end, there's a good chance you need to combine those logarithms together to see what the limits happen, what's happening with the limit on the inside of the logarithm there. That is a frequent thing that happens. All right. Yeah. Let's shift gears a bit. We should definitely talk about some of this trapezoid, midpoint, Simpsons rule stuff that we all need to talk about. Interesting. Sure, that's not right. Okay. We can certainly do more improper if you all want to, but let's do some trapezoid for a bit. So let's talk about just kind of the general context. So midpoint and trapezoid rule. So let's say we have a lake. And I know that I've measured cross sections of this lake. And sure. This length here is, now I'm going to make up some numbers that might not totally jive with my picture. That's all right. Sometimes pictures don't always tell the whole truth. This length here is 70 feet. This length here is 80 feet. This length here is 60 feet. This length here is 100 feet. This length here is 110 feet. We can pretend, right? And each of these sections are 10 feet from each other. So that's 10 feet, that's 10 feet, and so on. I want to estimate the area of this lake. And so one way I can do it is by using the midpoint rule. So I'm going to estimate the area. I suppose it's the surface area, whatever. Okay. So using the midpoint rule, and again, I'm gonna have to draw this. Now I have to draw this again. This is where it's gonna be a challenge because I'm gonna try and draw the same picture, but we all know how that goes. So, okay, not that close. Oh well, it happens. So here's what we're gonna do. So let's draw these same little sections here. This pen seems to be dying. Good. So the idea is that each of these can kind of act like midpoints. So, yeah, sorry, brain. That's not exact. Sure. Sorry, I'm seeing something. 1 second here. Let me think something real quick here. I've got different numbers. Sure. So, yeah, all right. So the idea is we're going to think of this height here as the midpoint of a rectangle like this. And the same idea here. This height here is the height of a rectangle whose midpoint is right there. And so on. Sorry, drawing is not always my strong suit. But essentially, the idea is that each of these rectangles, we can approximate or guess at their areas by saying, well, this whole thing here, that's a pretty, right? These rectangles seem like a pretty good approximation of that area, right? Like at least, I mean, with my very crude picture, it seems reasonable that, okay, we could say this has a base of 10, 10, 10, 10, 10. We could say, all right, well, the area is approximately all those bases times all those heights. 70 plus 80 plus 60 plus 100 plus 110. And that doesn't seem too far off. Now, my picture might be a little dicey at the end here. It's okay. And that, excuse me, that would be about, let's see, 7 plus 8 is 15, plus 6 is 21, 31, 41, 42. So 10 times 420, which would be 4,200 square feet. Okay. That's one way of approximating things. Essentially finding the midpoint of things, using that midpoint to give yourself a height, and then saying, well, the area of the rectangle is whatever your base is times that height, and then adding up all the rectangles. Or we also have something called the trapezoid rule, which now we're going to really see how well I can draw this picture again. It's always a crapshoot. So second way is using the trapezoid rule. So, all right, let's see. Yeah, okay, got even funkier looking. Okay, so it's like when you make a copy of a copy. So the idea now, we're gonna do the same sort of thing. We're gonna break this up into, still with those measurements, and let's see if I can try and line this up a little bit, just so we're not totally off base here. Sure. This is still 70, 80, 60, 100, 110. So the idea now is that for each of these, instead of using rectangles, we're going to use trapezoids. So we're going to draw the trapezoid that kind of goes with these four corners. So there's my trapezoid. And here's my trapezoid. Here's a trapezoid. And here's another trapezoid. And so now what we're going to do is use the trapezoid formula. So I never remember the trapezoid formula for anything in my life, but well, actually, that's right. After a lot of practice, I finally remember it. Basically, the formula for the area of a trapezoid is you take the average of the heights multiplied by the base. So the area of my trapezoid, or trapezoids, well, this first trapezoid is going to be the base times the average of the heights. And this next trapezoid is going to be the base times the average of the heights. And this next trapezoid is going to be the base times the average of the heights. And the last trapezoid is going to be the base times the average of the heights. Now, this kind of speaks to a formula, which is that you're going to get the base you can factor out. You can also factor out the 1/2. And then look what I've got. I've got 70. I've got 80 twice. I've got 60 twice. I've got 100 twice. And I've got 110 once. So I could add these all up. Let's see. So, I mean, I can't. Maybe I can add them all up. Let's find out. Let's see. I've got 10 over 2 times 70 plus 160 plus 120 plus 200 plus 110. Okay, fine. 70, 7, 16, 23, 35, 55, 66. Sure. So that's going to be 10 over 2 times 660. 6,600 divided by 2 is 3,300. I don't really care so much about the number, like it's just kind of an example to demonstrate that we have kind of these ideas of two different formulas, where one formula is essentially you take the base and you multiply it by the heights of all the midpoints. That's the midpoint rule. The other formula is you take the base, you divide it by 2, and then you multiply it by the first height plus twice all the middle heights and then plus the last height. So that kind of is leading us towards the following. That's not at all what I was looking for there. Sorry, yeah, question. That's a fair point. So my drawing is not excellent, is the real answer to that question. We would so we're gonna look at an example that's more accurate in just a moment. But yeah, you're right to ask about that, and the answer is my picture is crap. That's the real answer. So let's look at a real example here, or an example where we actually have a function. Let's go. Sure. So let's say we want to estimate the integral from 2 to 6 of natural log of x dx using first the midpoint rule with n equal to 4 rectangles. And so what I'm going to say is you can totally just memorize a formula for this. I think it's worth your time though to draw a picture. So let's draw a picture for what we've got. I should also point out, we could totally just integrate this, right? We know how to integrate natural log of x. It's something you can do with integration by parts. So we will actually see what the actual answer is as well, just because it's interesting. So if I draw my function here, natural log of x looks like this. And I'm going from 2 over to 6. So I'm trying to estimate this area. And if I do it using rectangles, so I'm going to divide this into 4 equal subsections. Luckily, 6 minus 2 is 4, so it divides really easily into 4 subsections. And then for each of these subsections, I'm going to pick the midpoint of that subsection to get the height of a rectangle. So the midpoint of 2 and 3 is 2.5, and there's the height of a rectangle. The midpoint of 3 and 4 is 3.5. There's my rectangle. The midpoint of 4 and 5 is 4.5. There's my rectangle. And finally, the midpoint of 5 and 6 is 5.5. So there's my rectangle. So using the midpoint rule, I could say, well, it looks like the area is going to be my base times the sum of my heights. So it's going to be f of 2.5 plus f of 3.5 plus f of 4.5 plus f of 5.5. In this specific example, my base is going to be 1. Right? Each of those rectangles has a base of 1. And their heights are going to be, well, I'm going to plug in 2.5 and get the natural log of 2.5, and then the natural log of 3.5, and then the natural log of 4.5, and the natural log of 5.5. Because I didn't actually calculate this ahead of time, let me grab the calculator. Remember the other day when I was looking for the natural log button on my calculator? It was literally like right there under the log button. I just could not see it for some reason. It was like, it's really like right there. I couldn't find it for the life of me. I don't know why. But let's calculate the natural log of 2.5 plus the natural log of 3.5 plus the natural log of 4.5 plus the natural log of 5.5. And we get approximately 5.377. Okay. All we're doing, so I should point out the very general formula for the midpoint rule is you're just taking your delta x, which is the base of each rectangle, where delta x is your b minus a divided by the number of rectangles. And you're multiplying that by f of the first midpoint plus f of the second midpoint, all the way to f of the nth midpoint. That's all we're doing. We're plugging in the midpoints of the function, you get the heights, and then we're multiplying those heights by the width of each rectangle. All right, let's do it using the trapezoid rule. So same idea, except now we're still going to break it up into 4 equal subsections. But instead of drawing rectangles, now we're going to draw trapezoids. Like here. Drawing the trapezoid is always a little more challenging because the function almost never wants me to do it that way. So I'm going to draw the straight line connecting those points, the straight line connecting those points, the straight line connecting those points. I've got this trapezoid, got this trapezoid, got this trapezoid, this trapezoid. Interesting question. Looking at what I've drawn, since this function is increasing, it looks like all my trapezoids are under the function, which is accurate. They will be, right? If your function, I should say, that's actually not accurate. It's because the function has downward concavity. If your function is opening downwards, then connecting any 2 points on it will be below the function. So looking at this, am I going to get an overestimate or an underestimate? Definitely an underestimate. Whereas my previous one, it's harder to tell if I have an under or an overestimate. I actually don't know by looking at it, honestly. Midpoint rule generally is usually a better estimate than the trapezoid rule, which you might feel, which I feel kind of weird, like, because it feels like we're using a shape that's better, but it's not as good an estimate. But it usually is easier to calculate because you have to find all the midpoints. So to calculate the trapezoid rule, we're going to say, okay, well, again, I'm trying to find the area, and it's going to be approximately the area of the first trapezoid, which is again 1/2, I should say, sure, the base, fine. The base times the average of the heights. So that's going to be, the average of those heights is f of 2 plus f of 3 over 2. And then the average of those heights is f of 3 plus f of 4 over 2. Plus f of 4 plus f of 5 over 2. Plus f of 5 plus f of 6 over 2. So what this ends up looking like is just like before, we can say that the area is approximately 1/2 the base. So that's 1 over 2. That's 1/2 of your base times f of 2 plus 2 times f of 3 plus 2 times f of 4 plus 2 times f of 5 plus 1 times f of 6. So trapezoid rule always has this pattern that I remember where it's your base over 2, and then it's a 1, 2, 2, 2, 2, 2, 2, 2, 2, 1 pattern, where the end ones have a coefficient of 1 and 1, and everything in the middle has a coefficient of 2. So more generally, before we finish this off, if I'm trying to find the trapezoid rule estimate with n rectangles, sorry, n trapezoids, it's going to be approximately, or it's going to equal your delta x over 2 times f of your first endpoint plus 2 times f of your next endpoint plus 2 times f of your next endpoint, all the way to 2 times f of your second to last endpoint, and then 1 times f of your last endpoint. Okay, so then in this particular problem, that's going to be approximately 1/2 times the natural log of 2 plus 2 times the natural log of 3 plus 2 times the natural log of 4 plus 2 times the natural log of 5 plus the natural log of 6, which is going to be approximately 5.34. Okay. Something I also just want to point out, you get more terms when you do the trapezoid rule. So when I do the midpoint rule, there are 4 intervals. I have 4 rectangles. I have 1, 2, 3, 4 heights. But when I do the trapezoid rule, there are 4 trapezoids, but I'm averaging each of their heights. So I get 2 heights here, 2 heights here, 2 heights here, 2 heights here. 3 of them overlap, so I get 1, 2, 3, 4, 5 different terms I have to get. So the trapezoid rule is always going to have 1 more term added than the midpoint rule. And that's just something people find that a little confusing. They're like, why am I getting more terms here? That's why. So then to actually find out, to compare it with the actual value. So what's the actual value? How do we integrate natural log of x? Have we actually done it in class? I feel like we might not have actually done it. Oh, we did? Okay. Do you remember what it is?
X, natural log of x minus x.
Good, yeah, right on. So this is definitely x natural log of x minus x from 2 to 6. I'm certainly happy to do it again if anyone wants. So just in case, I'm not going to do it again unless people want me to, but in case you forgot how to do it, you let u equal natural log of x, your du is 1 over x, your dv is dx, and your v is x. And then you integrate backwards. So this is going to end up being 6 natural log of 6 minus 6 minus 2 natural log of 2 minus 2, which is approximately, using a calculator, 5.36. So our error using the trapezoid method, which people usually write as E sub t, is equal to our actual value minus our estimate, which was 5.34, which is about 0.02. People usually throw this an absolute value around this just so that you can say that your error is a positive number, but you don't have to. Yeah, notably our estimate was under. Using the midpoint rule is, well, let's see, our midpoint rule estimate, I don't remember what it was, it's 5.377. Excuse me, so that's approximately negative 0.0177. So a slightly better estimate. Not surprising to me, right? The midpoint rule usually gives a better estimate than the trapezoid rule. What else to say about this? I would, again, probably put absolute values around each of these. It usually makes sense to talk about the error being a positive number. So when you're trying to use the trapezoid method or the midpoint, sorry, the trapezoid rule or the midpoint rule to estimate error, to estimate the area under a curve, that's how you do it. There is also one other method called Simpson's method, which is kind of funky. Simpson's method, so instead of using trapezoids or using rectangles to estimate area, what you're actually doing with Simpson's method is you're using parabolas. So the idea is, I know we're not actually like drawing it, as it's not my forte, but if you're doing Simpson's method, the idea is that you're saying, I've got some function like the natural log of x, sure, let's go with it. And if I break it up into 4 little sections here, what I'm going to do is in these first 2 intervals, I'm going to say, well, I can find some parabola that goes through those 3 points. And maybe it looks, I don't know, maybe it looks like that. Maybe that's my parabola there. And so I'm going to use the area under that parabola to estimate the area under there. And then we do the same thing for these 3 points. I'm going to say, well, for these 3 points, there's some parabola. And it is true. There's a theorem in math that says through any 3 non-collinear points, you can always find a parabola. It's a true theorem, which you don't have to say it's true if it's a theorem, because if it's a theorem, that means someone has proven it. But there's a parabola that goes through those as well. So again, you can also find the area under those in the same sort of way. And then that's actually supposed to give an even better approximation of the area under the curve. So usually Simpson's method is the best approximator of area under a curve. You can derive this formula. No one should derive this formula. But let's talk about, yeah, another example. Actually, let's actually we should use Simpson's rule here. So using Simpson's rule, actually, before we use Simpson's rule, let's write down all the rules, just so we know. Apologies, sorry. So midpoint rule. So midpoint rule using n rectangles is going to be, we usually write it as m sub n, and it's your delta x times f of the first midpoint plus f of the second midpoint, all the way to f of the last midpoint. And before I go any further, let me actually draw what I mean. So this is my interval. I'm not going to, well, you could say, okay, here, right here. Here's my function. I'm going from, say, here to here. And I'm breaking it up into n subintervals. So here's my first subinterval, my second, my third, all the way up to my last subinterval and my second to last subinterval. Can I see your symptom survey, please? So this value here, right? This is my x sub 0. And then this is my first endpoint, my second endpoint, my third endpoint, all the way up to this b is my nth right endpoint. Oh. Okay, that's fine. That's my n minus 1. That's my n minus 2. So then the midpoint of these first two, right, that right there, that's my x1 bar. That right there, that's my x2 bar. That right there, that's my x3 bar. All the way to that last one there, that's my xn bar. So that's what I mean when I'm writing that notation, right? We're using those midpoints. And then for the trapezoid rule using n rectangles, it's going to be your delta x divided by 2, and then f of x naught plus 2 times f of x1 plus 2 times f of x2 plus all the way to, thanks, appreciate it, 2 times f of x sub n minus 1 plus 1 times f of xn. And you might again notice this first thing we're calculating has n terms, right? 1, 2, 3, 4, 5, 6, 7, n, whereas the second one has n plus 1 terms. 0, 1, 2, 3, 4, all the way to n. All right, so then finally, using Simpson's rule, I always forget what you divide by, to be honest with Simpson's rule. For Simpson's rule, Simpson's rule, I'm not remembering what you divide by. Oh yeah, okay, that's what I thought. All right, good. You're gonna get delta x over 3 times. So here's the pattern. Trapezoid rule is 1, 2, 2, 2, 2, 2, 2, 2, 2, 2 forever until you get the last one, then 1. Simpson's rule is 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. So it's 1s and then 4s and then alternates. So it's 1 times f of x naught plus 2 times f of, sorry, I said 4 and then I wrote 2, plus 4 times f of x1 plus 2 times f of x2 plus 4 times f of x3, all the way to the very last 3 terms. The third to last term is 2 times f of x sub n minus 2, and then a 4 times f of x sub n minus 1, and then a 1 times f of x sub n. So that's Simpson's rule. It's not any worse than the trapezoid rule. There's one thing that has to be true for Simpson's rule, and that is for Simpson's rule, your n must be even. If your n, like for example, if n is 6, okay, I get 1 f of x naught, 4 f of x1, 2 f of x2, 4 f of x3, 2 f of x4, 4 f of x5, and then 1 f of x6. But if my n was 5, I wouldn't be able to get the right. I wouldn't have enough terms to get the 1, 4, 2, 4, 2, 4, 1 pattern at the end. Or you can think about it from what we were saying before with the parabolas, right? Whenever you're using Simpson's rule, you're taking 2 whole sections to draw 1 section of a parabola over. So you have to have an even number of sections. So your n has to be even. Okay. And then what I wanted to say was, in just in case I didn't say it before, your delta x is just the width of each subinterval. which is your b minus a divided by n. Cool. So then we could use Simpson's rule to also approximate the integral we did before, just for comparison's sake. So Simpson's rule to approximate the integral from 2 to 6 of the natural log of x dx. And let's see what we get. So now I'm just, oh yeah, question. It's a more accurate estimator. That's really why. Simpson's rule is actually like the weighted average of the other two rules, which is kind of weird. Like I've never really thought of it that way, but books usually mention that like it's like 1/3 of one of them plus 2/3 of the other one, which is kind of interesting. So yeah, but yeah, that's why you'd want to use this because it's a more accurate estimate. So if we do it here, then we're going to get s sub 4 equal to, so I'm really just going to throw the rule at it, right? I'm going to be like, okay, it's going to be delta x over 3 times 1 times f of x 0. All right, I need to ask you guys to leave. You're being too loud. You're being distracting. No, really, I'm asking you to leave. Don't come in. Plus 4 times f of x1, plus 2 times f of x2, plus 4 times f of x3, plus 1 times f of x4. So our delta x here is 6 minus 2 over 4, which is 1. And then we just get the usual points. So we're going to get s sub 4 equal to 1/3 times the natural log of 2 plus 4 times the natural log of 3 plus 2 times the natural log of 4 plus 4 times the natural log of 5 plus 1 times the natural log of 6. And this ends up being approximately something I didn't already calculate ahead of time. So let's calculate it real quick. We get 1 divided by 3 times the gross numbers here. Let's see. All right. And so we got natural log of 2 plus 4. So the thing about these questions that I think is really silly is like you're being asked to approximate this thing, right? And then you're using a calculator to approximate it. So why not just use a calculator to do the original approximation in the first place? So anyway, natural log of 2 plus 4 natural log of 3 plus 2 natural log of 4 plus 4 natural log. And it's really fun to watch me do this, right? It's like super exciting. What's that? I know, right? So we're working towards what we're actually doing. So you can use, right? So the point of these questions really isn't that we're going to do these approximations. We're talking about them to kind of get to the next part, which you can totally do mostly without a calculator. Doing this, you get approximately 5.363, which, if we go back to what our previous thing was, is a slightly better estimate, but not a whole lot. So it makes you kind of feel like, what's the point? So the point is this, right? And I might say, you're right. What is the point? We've done this for problems that I know how to integrate. Well, some functions can't be integrated. So for example, it might actually make sense to say, I want to estimate the integral from 0 to 2 of e to the negative x squared dx using any of the rules, using n equal to 6 with midpoint or trap or Simpson's rule. And the reason this might be useful is that this thing actually cannot be integrated. There is no antiderivative of e to the negative x squared. Same is true for like sine of x squared. There's lots and lots of functions that can be. And this function we actually really care about because this is the function slightly modified that is the bell curve in statistics, which is something we actually care about knowing the area under. It's not just like made up, right? There's actually reasons for knowing this. So this is something we would actually want to use this for. But I really don't want to put you through doing this again, right? So we could totally like, so just for example, like if I was going to do this using n equals 6, we're going to write out the formulas, but we're not actually going to calculate them because. So using the midpoint. Oh, midpoint's gonna suck. So the thing that's never fun about midpoint is you have to calculate your endpoints and then calculate the midpoints of those. So let me ask you all, what's my width of my rectangle? What's my delta x in this particular problem? Smaller than 1, right? I broke it, I did 6 because, right, I'm not kind. So my delta x is going to be what? Yeah. Okay. To find the midpoints, I really find it easiest to draw out the x-axis. You don't need to draw out the function, but I'm going to draw out the x-axis and be like, okay, I'm starting at 0. I'm going to 2. I'm breaking it up into 6 sections. I know my width is 1/3, so I know that all these points are 1/3, 2/3, 3/3, 4/3, 5/3. And then the midpoints are halfway between. So what's the midpoint of 0 and 1/3? Well, 1/6, right? And then instead of finding the midpoints of each of the other ones, you could find the midpoint of 1/3 and 2/3 by adding them together and dividing by 2. Or you could just be like, I know it's going to be exactly 1/3 away. And 1/6 plus 2/6 is going to give me 3/6. And then if I add another 2/3, I'm going to get 5/6. If I add another 2/6, I'm going to get 5/6. If I add another 2/6, I'm going to get 7/6. If I add another 2/6, I'm going to get 9/6. I'm going to add another 2/6, I'm going to get 11/6. So that's how I would find the midpoints. I feel like that's the easiest way of doing it. If the numbers are nicer, you don't have to work so hard, but I feel like these numbers are ugly enough that we should do it this way. And then my area is going to be approximately my delta x times f of the first midpoint plus f of all the other midpoints up until f of the last midpoint. So that's going to be, in this particular case, 1/3 times e to the, so this is where things are, even just writing it out, it's kind of gross, right? My function is e to the negative x squared. So it's going to be e to the negative 1/6 squared plus e to the negative 3/6 squared. Yes, I know I could reduce that fraction. I don't want to. E to the negative 5/6 squared, e to the negative 7/6 squared, e to the negative 9/6 squared, e to the negative 11/6 squared. That would be my midpoint rule approximation. And if web work asked me to do this, that's what I would write in web work. Actually, if I had to do this in web work, I would do the squaring instead of writing square. So I would write my answer as 1/3 times e to the negative 1/36 plus e to the negative 1/4 plus e to the negative 25/36 plus e to the negative 49. Right? I would square those out because typing out that is easier than typing in something squared, I think. Can I ask you to stay outside, please? Right, but this is a class that's not your class right now, so please stay outside. Like, come on. Sorry, I know I'm a little, I'm feeling a little heated. I should maybe calm down a little bit. All right, so we can also use this using the trapezoid rule. Same idea, right? You're going to do your delta x over 2, and then it's to be 1 f of x naught plus 2 f of x1, et cetera, et cetera, et cetera. 2 f of xn minus 1 plus f of xn. The nice thing about the trapezoid rule is that you don't have to find all these midpoints, right? So that's kind of why people, even though the trapezoid rule is a less good estimate, it's why it often gets used, because we can just be like, oh, we're going to have, 1/3 divided by 2 times f of x naught, which is just f of 0. So we're going to get e to the 0. And then 2 times e to the negative 1/3 squared plus 2 times e to the negative 2/3 squared plus 2 times e to the negative 3/3 squared, and so on. But a lot of these are just an exercise in pain, where they're just like, do this thing that's kind of gross. And then Simpson's rule would be very much the same idea. Simpson's rule is going to be your delta x divided by 3, and then it's going to be almost the same thing I've written here, except instead of 1 2 2 2 2 2 2 2 2 1, it's going to be 1 4 2 4 2 4 2 4 2 4 1. which I guess I'll write out, even though it seems silly. Oops, that should be a 4. All right. Great. So that's how you estimate these things. But here's what we're actually going to do with them now. Probably no one's going to ask you to do this on a test, I hope. Or if they do, they will make it not terrible and they'll give you a function that's relatively easy to throw things into. What we do often talk about, though, is how to estimate the error. So we have error estimates for each of these formulas. Back just a moment here. So using the trapezoid rule, if you use the trapezoid rule, you can say that the maximum error is given by the following formula: b minus a cubed over 12n squared times the absolute value of the maximum of the second derivative of your function, where x is between your endpoints. So let's look at an example. Let's say I wanted to pretend like I'm going to estimate this integral, the integral from -2 to 0 of e to the x squared. And I want to, after I do the estimate, which I'm not actually going to do, I want to know, what is the most my estimate could be off by? All right. Well, I'm going to calculate this. So the most my error can be off by is going to be, and we usually write this as E sub t. The error using the trapezoid method is going to be less than or equal to, so b minus a, that's going to be 0 minus -2 cubed over 12n squared. Oh, what n did I use? So what's the most my estimate can be off by if I use n equal to, let's say n equal to 4. So I broke this up into 4 subsections. So that's going to be over 12 times 4 squared. And then here is where things get interesting. That's the maximum of the second derivative of your function over the interval. So let's find the second derivative. The first derivative is going to be e to the x squared times 2x. The second derivative is going to be product rule, e to the x squared times 2 plus e to the x squared times 2x times 2x. Now, here's what usually happens. People don't actually find where this is exactly maximized. They say, I can make some estimates. Between -2 and 0, e to the x squared is going to be biggest. I wanted to do no. Sorry, I meant for this to be e to the -x squared. Let's fix that. So sorry, my second derivative is actually then e to the -x squared times a -2x. And this other second derivative is an e to the x squared times a -2 plus an e to the -x squared times a -2x times -2x. Sorry for that. So on the interval from 0 to -2, or I should say -2 to 0, what's the biggest e to the -x squared can be? Well, if I plug in -2, I get e to the -4, which is small. If I plug in 0, I get e to the 0, which is 1. E to the -x squared kind of looks like this. It's not my best picture, but it actually, I mean, actually looks kind of like a bell curve. So the biggest it can be is going to be when I plug in 0. So I know for sure that this is less than or equal to, that's going to be 1. This part here, I'm going to say, I'm going to put some absolute values around this at some point. So I'm going to put a 2 there. The biggest this can be is also 1. And the biggest -2 times, well, the biggest x can be is, or the furthest away from 0 x can be is -2. The biggest this can be is essentially -2 times -2. Basically, you make every piece as big as you can, if it's not obvious how big it can be. So this is going to be less than or equal to 2 plus 16, which is 18. Now that's not perfect, right? That is definitely an overestimate of how big this actually can be, but this is what people do every time. So I would definitely say, oh, that's going to be 18. That's the biggest that can be. And then we would simplify this. We would get 8 times 18 over 12 times 16. We would cancel some stuff. So I end up getting 3/4. So that's the biggest my error could be using this method. It's probably smaller than that. This is an upper bound on what the error can be.
Which one did you use for 2x minus 2x as 3?
Sure. So let me revisit. Yeah, let's look at that again just a little bit closer. So, right, we were saying we want to find the maximum value of the absolute value of the second derivative. So we're trying to find the maximum value of the absolute value of e to the negative x squared times -2 plus e to the negative x squared times -2x squared is 4x squared. And so what I'm really doing here is I'm using something called the triangle inequality, which is that if you have the absolute value of some quantity, this is going to be less than or equal to the absolute value of each piece separately. Basically, we're basically making each piece as big as we can on their own. So that's what I'm saying. And so then what's the biggest this piece can be? Well, when x is between -2 and 0, the biggest this can be is when x is 0.
What would it be if x is equal to -2?
So then it'd be, so if x equals 0, we're going to get e to the 0 squared times -2, which is going to be e to the 0 times -2, which is 2. If e is -2, then I'm going to get e to the -2 squared times -2, which is e to the -4 times -2, which is the absolute value of -2 over e to the 4th, which is much, much smaller, right? E to the 4th is, I don't know, 60, 70-ish, something like, right? Let's say e is 3, 3 to the 4th is 81, it's less. So this is like 2 over 60 or 2 over 70. This is much, much, much smaller than 2. So that's why how we're doing this. We're picking x to be 0 so that we can kind of say, okay, well, that's the biggest it can be. And then we're doing the same idea here, except here we're really saying, well, the biggest this piece can be is when x is 0, and you get e to the 0, which is 1. And the biggest this piece can be is when x is equal to -2, so you get 4 times 4. So we're making each little part as big as it can be so that the whole thing is guaranteed to be bigger than it could possibly be. Okay, let's look at one more example. So the question that I would ask on a test if I had to ask a question about this stuff, because usually a lot of people would be like, I'm not going to ask any test questions about this because it's a giant pain in the butt for everyone to do and for everyone to grade. But the kind of question that often gets asked if they're going to ask one is, find the n, the number of intervals you need so that the trapezoid rule estimate of this interval, let's change up to the interval from 0 to 1 of e to the negative x squared dx, is accurate to within 1/1000. That is 9 times out of 10 the type of question people like to ask or are willing to ask about this kind of topic. So we know that the error using the trapezoid method is less than or equal to b minus a cubed over 12n squared times the maximum of the second derivative of the function over the interval, in this case, from 0 to 1. And we want that to be less than 1/1000. Okay, it's not too bad. So what are we trying to find here? N. So we know that we're not actually going to plug in anything for n, right? That's going to be left and everything else is going to be plugged in for. So we're going to get that we look at this inequality, we're going to get b minus a, so that's 1 minus 0, so 1 cubed over 12n squared. The max, let's talk about the maximum of my second derivative. So my first derivative is, well, it's the same as before, right? It's e to the negative x squared times negative 2x. And my second derivative is e to the negative x squared times negative 2x squared plus e to the negative x squared times a negative 2. So I could do a little bit of simplifying, I suppose, and say this is going to be equal to e to the negative x squared times 4x squared minus 2. And then what's the biggest this can be? Well, the biggest this can be is when x is 0. The biggest this can be is when x is 1. So the biggest is going to be e to the 0 times 4 times 1 minus 2, which is 2. We probably in the previous problem could have kept things together a little more than I did, but it wasn't unsafe to do what I did. So it was still perfectly fine. We probably could have gotten like 14 instead of 18 as our value for our f double prime. So then here we're going to say, all right, this whole thing, that's 2. And we want this to be less than 1/1000. So then we're going to solve for n. So let's see. I've got 2 over 12n squared less than 1/1000. I would cross multiply. So 2000 is less than 12n squared. I really didn't need the 12 over there, so let's put the 12 back. So n squared is bigger than 2000 over 12. 2000 over 12 is approximately, or I should say, let's take the square root. So n has to be bigger than the square root of 2000 over 12, which is approximately 12.9. So I'm going to pick for n, if n has to be bigger than 12.9. Yes, exactly. I have to pick the next biggest integer value. So I would say, okay, n has to be 13. We'll talk next time, if we want to, about how if it's Simpson's rule, like, so if I had done this one, if this had been the same problem, but it was Simpson's rule instead of Trapezoid rule, it's a different formula. But if I had gotten n bigger than or equal to 12.9, I would have said that n had to be 14. Because n has to be even using Simpson's rule. Yeah. So I suppose that how it's phrased. So in this case, it would be n equal to 13.